On Friday, March 11th, an earthquake measuring 9.0 on the Richter scale occurred off the east coast of Honshu, Japan. One of the largest earthquakes ever recorded, shockwaves ravaged Japanese buildings, homes, and infrastructure, and triggered a 30-foot tsunami that surged several kilometers inland, leaving hundreds dead and cities in ruins. In Fukushima, just over 100 miles away from the epicenter, tsunami waves damaged diesel fuel generators that powered the cooling system for reactors at the Fukushima Daiichi nuclear power plant, leading to several fires occurring within the plant as well as 3 large hydrogen explosions. These damages in turn caused large amounts of the radionuclides iodine-131, cesium-134, and cesium-137 to be released as steam and in leaking coolant water. The radionuclides released as steam were dispersed via wind flow and have settled into soil and bodies of water, thus contaminating food and drinking water sources for the Japanese people.
In response to the radionuclide contamination of Japanese drinking water, Team Tsunami has designed an RO unit operation aimed specifically at removing these contaminants from the drinking water reservoir for a city of 400,000 people. Iodine-131 is a radioisotope of iodine. It has a radioactive decay half-life of 8 days. It is a product of uranium and plutonium fission occurring in nuclear power plants. It is notable for causing mutation and death in thyroid cells. Worldwide measurements of iodine-131 indicate that the release from the Fukushima power plant are on the same order of magnitude as the release from the Chernobyl disaster in 1986, roughly 1.3 times 10 to the 17th becquerels per day.
Our semi-permeable membrane is composed of 3 parts, a polyester base and polysulfone layer, each acting only as support for a thin composite polyamide membrane skin that is formed by polymerizing amide and carboxylic acid chlorine monomers on the supporting polysulfone layer. This membrane skin is responsible for allowing permeate water to pass through while utilizing size exclusion and adsorbed surface water layer to physically remove concentrate. Our membrane operates at a particle removal range of 1 to 0.1 nanometers. Individual elements are formed by layering the membrane with feedwater spacers and winding it into a cylinder.
Our design calls for using large diameter membranes. Large diameter membranes are classified as larger than 203 millimeters. The Mega Magnum membranes made by Koch are 457 millimeters by 1049 millimeters high and can replace 7 standard membranes. They offer several advantages over the smaller size. Because of the larger size, significantly fewer membranes are required. The RO plants are also more compact and simpler, with fewer pressure vessels, connecting joints, and pipes. This leads to lower capital costs plus cost saving for maintenance and operation. Membranes operate within a pressure vessel, a large steel pipe which can withstand the high pressure. 5 Mega Magnum membranes are loaded into one pressure vessel and pressurized to 1800 kilopascals. Our design calls for 3 pressure vessels to be loaded into racks. The racks are then treated as individual units with its own pump and feed line, able to be taken offline individually. This allows for easier maintenance to be conducted.
Since RO filtration is highly selective and occurs under high pressures, a high-quality feed water is necessary to prevent the filter from becoming clogged with scale, biofilms, or excess concentrates. Therefore, several pretreatment steps are taken, starting with a sand filter, followed by micro and ultrafiltration. Next, the water is treated with anti-scalant acid, both preventative measures against scale formation. Finally, prior to entering the RO unit, the water is disinfected via UV radiation as opposed to chlorination because residual chlorine corrodes the RO polyamide membrane. Based on our pretreatment operations, we have assumed that the particles greater than 5 nanometers have been removed from our feed water prior to entering the RO unit.
When sizing the reverse osmosis plants, we made several assumptions. The radioactivity of the feed was 200 becquerels per liter, which is the average concentration of iodine-131 in Tokyo's drinking water. We need to treat the drinking water to less than 10 becquerels per liter, which is the maximum advised by the World Health Organization for drinking water quality. In order to get it to that level, we would need to reduce it by 95%. The US EPA states that reverse osmosis can remove up to 99% of radionuclides from drinking water, so we made the assumption that there is a 97% radionuclide reduction, giving a radioactivity in the permeate of 6 becquerels per liter. We found from the United Nations Development Program that the per capita water use in Japan is 374 liters per day. We're designing a plant to treat the water for 400,000 people, and we included a 10% safety factor. The recovery rate we assume to be 95% because the inflow is relatively pure. We also assumed a water mass transfer coefficient of 9 times 10 to the negative 9th seconds per meter because of the specific membrane that we're using, and the operating pressure is 1800 kilopascals because we are using special low pressure membranes. In order to size the reverse osmosis membranes, we made some calculations. The first calculation that we used is the radioactivity to mass equation. Using 200 becquerels per liter in, we got a feed concentration of 4.346 times 10 to the negative 11th grams per cubic meter, and our permeate concentration would be 3% of that, and our flow rate for the permeate we found using the 10% sizing factor was 1.905 cubic meters per second, and the flow rate for the feed was that divided by 95%. To find the water flux rate, we multiply the water mass transfer coefficient times the operating pressure, and to find the final total membrane area, we divide the permeate flow rate divided by the water flux rate, which gives us a total of 117,600 square meters.
Using the required area, we found the total number of elements we would need. Our system will require 420 elements with 5 membranes per pressure vessel, bringing the total to 84 pressure vessels. There will be 3 pressure vessels per rack, bringing the total number of racks to 28.